I'm going to talk about cosmology and also a recent problem in cosmology known as the Hubble tension, and then how future observatories, we hope, are going to help us learn more about it. So it's been, by any measure, a tremendous 25 years or so in cosmology. We've had a great deal of progress through critical observations obtained over that time, particularly measurements of the recent expansion history, the Big Bang afterglow, known as the CMB, Big Bang nucleosynthesis, in large-scale structure, coupled with theoretical physics. We have a standard model now, known as lambda CDM, and it's a very powerful model. It matches the data, most of the data that we have, but about 96% of it is still not deeply understood by us. And so it is possible that there will be surprises, particularly from the dark sector of dark matter and dark energy. And so we continue to observe. Now, one of the key features of our universe is that it's expanding, and by measuring the expansion rate and the expansion history, we can learn about the composition and the age of our universe. We would like to just directly measure how the scale of the universe changes with time, but those observables are not accessible to us, so instead we measure distances in redshifts, which are equivalent, for objects we can see, known as standard candles. Brian Schmidt and I, along with Saul Perlmutter, made observations of type 1a supernovae as those standard candles. And aside from seeing the universe expanding, the present rate, which is known as the Hubble constant, we also measured the past rate, measured changes in the expansion rate, and saw that the expansion is now speeding up or accelerating. This was what we shared the Nobel Prize for in 2011. Now, the simplest form of lambda CDM that still matches this basic prescription looks like you see there, like a ski jump, sort of. There's a downhill part, which the expansion rate is slowing down. That's when the universe is dominated by dark matter. That's critical because dark matter has to win at some point to form structures that we see. But as the universe expands, that matter is diluted. And so dark energy, something like a cosmological constant or a fairly static level of energy, will eventually come to dominate and the universe will accelerate. But the question is, for us really, is the simplest form that this can take, which is what we use mathematically, is that right? Or is it not so simple, and are there clues about the nature of dark matter and dark energy that we could gather by getting additional measurements of this expansion history, only some of which has ever been probed? Now, one of the more rigorous end-to-end tests of this entire expansion history comes from measuring and predicting the value of the Hubble constant. And the way this works is we can look at the very early universe, see the cosmic microwave background, and by comparing the angular size of fluctuations in the spectrum to the physical size of fluctuations as modeled by lambda CDM, we can set or calibrate the 6 free parameters of the model, and then use the now calibrated model to predict that ski jump shape, the expansion history, to the present time and the value today of the Hubble constant. And when this is done, most recently with Planck and other ground-based experiments, you see a relatively low value, 67.2 or whatnot. The other method, which is more direct, following the same way that Hubble and Brian and I and others have done, is to measure distances locally and redshifts locally from standard candles and directly measure the Hubble constant from its definition. Funny thing doing this, the two don't match, and this has been simmering for a decade. As I would say, for a decade we've seen it not matching, and better data has caused this discrepancy to grow to pass 5 sigma. This is known as the Hubble tension. What I'm showing there on the right is some of the best data from the local measurements and from the CMB. It looks not only very significant, it looks reliable based on many different measurements of it, and it kind of has our community in a tizzy. We had a great conference in 2019 that David Gross and others hosted, And he told us at the conference that we could start calling it a crisis since it was 5 sigma. But I think tension works better because it's more a state of mind and feeling of our community. So I've spent the last couple of years really scrutinizing the tension from the observational standpoint, using the James Webb Space Telescope, which has extremely good resolution. We were able to return to the measurements made with Hubble, but much better. And the JWST data confirms the Hubble data, strengthens the tension. And then in the last year, a large group of us, about 40, gathered to review all the distance measurements locally. See, there are many ways to get to the Hubble constant, many other distance indicators. Some of them are correlated, some of them are not. And if you can write down the proper covariance matrix, which was the exercise for the week, you can combine all of this information. When you do that, you get an even tighter constraint. We're up to about 7 sigma, so I don't know what David's word for that is, but it's a lot. But more importantly, as you see on the right, we can really do sensitivity tests. We can eliminate any single tool that is used to estimate the Hubble constant. Supernovae, Cepheids, whatever it is, the answer does not change significantly. There's a very good chi-square, very good internal agreement, and so it seems that the universe has still another surprise for us. So on my last slide, I'll just say that there are many facilities, really an armada of new facilities, both recent and upcoming, that while they're not tuned for this problem, can't help but provide a lot of important information about it. And I think it's a great time to be doing observational cosmology. Thank you.
I'm going to talk about particle physics measurements that can be made with astrophysical information, the particle astrophysics region. And what we're dealing with is the ability to make these measurements in a deep underground environment, 2 kilometers down. We have one laboratory 2 kilometers down in Canada, and I'm going to emphasize several of the experiments we're doing there, but they're typical of a wide range of measurements being made around the world in similar underground laboratories, including the other one that's as deep, which just has opened in China. What we measure typically is properties of neutrinos, and we are searching for dark matter particles that potentially are interacting with our detectors because we know the dark matter is influencing the shape of our galaxy, the Milky Way, and so we know it's there. Our measurement of neutrinos with the Sudbury Neutrino Observatory, which is what won the Nobel Prize, were capable of showing that neutrinos have a finite mass. They confirmed the reactions that were thought to be powering the sun, which lead on to reactions that produce carbon, nitrogen, and oxygen, and also validated the sort of calculations that are done for fusion power here on Earth. Now, the sort of things that we're talking about when we discuss this Big Bang as the way in which the universe has evolved since the universe has evolved since the Big Bang are really existential questions. They're not questions of, how did humans evolve? They're questions of how did everything evolve? They're the sort of questions that, the ancient philosophers were interested in. And, in the overall fabric of human endeavor, addressing these sorts of questions are something that humans have always wondered about. And so we hope to provide some additional clues as to what's happening. Now, as I said, going back to first principles, particles are what we're going to be dealing with, and I'm talking about some unusual ones here, particularly neutrinos and dark matter. Just to remind you, the standard model of elementary particles, if you just deal with the components that make up ordinary matter, you have quarks, which in groups of 3 make up neutrons and protons, which are in the nucleus of an atom surrounded by electrons, giving you the way in which our world we're familiar with works. Neutrinos are unusual. They feel only the weak interaction. They can penetrate through enormous amounts of matter. They are produced in very large quantities in the sun by the nuclear reactions, and they are produced to some degree in radioactivity here on Earth. But that part of the set of particles is only part of the whole. Other heavier particles have been observed in cosmic rays and in accelerator experiments, and you can see in the quarks, neutrinos, and electron-like particles, you have, for example, muons and taus similar to electrons but heavier. The other thing you need to know is that it has been observed that essentially every one of these particles has an antimatter particle, which has the opposite, essentially, quantum numbers, and which, if it encounters its ordinary matter partner, annihilates with it, leaving pure energy. So the reason I bring that up is that in the Big Bang, it is thought that things go in the opposite direction. It is thought that pure energy is converted into equal amounts of matter and antimatter. And that's one of the questions that we wonder about, because you don't see very much antimatter in this particular room, which is just as well. Dark matter doesn't fit into any of these standard roles that particles take. There are several forms it can take. One of them that we are looking for is ones where it is heavy particles that can bang into our detectors and perhaps be detected. The Big Bang theory, if you think of it from a more particulate point of view, starts with the bang that produced equal numbers of all the particles and antiparticles, enormous amount of energy available. After about a microsecond, the cooling effect of the expansion allows quarks to combine into protons and neutrons. After about 3 minutes, you have them combining to form nuclei, and after about 300,000 years, you get neutral atoms, which are wonderful in the sense that at that point you can see the light because it's transparent, and that's the cosmic microwave background that Adam just described. After about 1 billion years, you have the formation of structure, and that is where this material called dark matter comes into the question, because the models require it in order for that to happen. We're also doing measurements that may give us an answer as to what happened to all the antimatter. We're doing it with understanding properties of neutrinos in our underground laboratories, and accelerators like Fermilab and JParc are looking at large distance oscillations of neutrinos that could tell us the difference between matter and antimatter, neutrinos and antineutrinos. This is our underground laboratory, 2 kilometers deep in an active nickel mine, ultra clean everywhere. Enormous number of experiments, 5 or 6 different experiments with different materials being presented in an ultra low radioactivity background, such that we could see, even if very few events per year result in a signal. Plus the experiment on the far left, Snow Plus, which is a large-scale experiment. This is the size of a 10-story building, in which we are going to insert a potential rare radioactivity that can tell us properties of neutrinos, in particular whether or not they are their own antiparticle. Even the dark matter experiments are a large scale. This is use of liquid argon, which has another hook that enables you to get rid of radioactivity, in that the recoiling nuclei from the dark matter will give light in 10 nanoseconds and radioactivity 10 microseconds. A lot of experiments around the world that are doing both of these types of experiments. These are the ones we do in Canada. And the overall picture, as Adam had on one of his slides, shows us, at least at the early stage, dark energy at 70%, us at only 4%, dark matter at 26%. So in the Donald Rumsfeld sense, there's still lots of unknowns in this particular field. However, the fact that we are able to combine experiments from all across the world in an open way, the benefits of basic science being an open environment, and we can work together across the world, is what's made progress here, and which we hope makes progress in a lot of areas, including the medical area that we heard in the earlier session. Thank you very much.
So I'm going to talk about almost infinitesimal pulse durations. That is the goal of those of us who work in short pulse laser science, how to get ever shorter pulses. The shortest pulses that come straight from a laser are 5 femtoseconds. and a femtosecond is 15 orders of magnitude shorter than a second. So compared to a second, that's infinitesimal. And so the other part of it, though, is if for those of us who want to make really short pulses, it means we have to have as close to infinite spectrum as we can. Now, that one's a little bit harder to call infinite, but this just shows that if you had an infinitesimally small spectrum, single color, it would last forever, and it would be infinitely long. And the opposite is also true. If you want a really short pulses, shown by the black line here, you have to add a whole lot of colors together. So this is what's known as Fourier transform theory. This is what all short pulse laser people die on. This is also what my quantum colleagues would call the Heisenberg uncertainty principle, but Fourier came before Heisenberg. And as my colleague Bill Phillips said yesterday, what quantum brought us is that even particles are waves, so we all have to live with Fourier transform theory. So that's what I'm going to tell you about. It's not enough, though, for us to have all the colors that we want. Obviously, a very, very bright light is shining on me with all the colors, probably from the UV, except that should be stopped by the glass, to the infrared. So all the colors are coming out of that very bright light shining in my eyes, but they're not all phased together. And so really what that is a whole lot of light noise, okay? And so it would just look random, and you wouldn't have nice short pulses, which is what we want. So it's not about just getting a lot of pulses or a lot of colors, it's about having control, all right? That's really what my field's about, is control. So I'm just showing here 10 colors, and they're all related in that the fundamental frequency has a period t, and so that frequency is 1 over the period, 1 over t, and I'm just taking harmonics of that, from 1 over t, 2 over t, all the way to 10 over t. So the whole spectrum is 10 times 1 over t, and if you add those all together, you get what's at the bottom, and it's a series of pulses, all right? And the pulse period is t, which is 1 over the separation of the frequencies, and how short the pulse is 1 over the whole spectrum. Since the whole spectrum is 10 times 1 over t, it's 1/10 of a t. Okay, so the shorter you want the pulse, the broader you want your spectrum. That's the point. And just to show, again, something else that comes up, especially for those of us who want to make short pulses to make high intensities, we would like it really to all be in one pulse. That means that we want the separation of the frequencies to be as small as possible to separate how fast these pulses come. You can see by having the same overall spectrum, but only 5 of the colors, so they're now separated by 2 over t, we start having pulses half the distance apart. So we have twice as many pulses, so the energy in each pulse would be halved. So we don't usually want that. If again, though, you take 5 of the colors, but now you see that we only span half of the total spectrum, our pulses do get twice as long. So that is Fourier transform theory explained. If the shorter the pulse, the broader the spectrum. And again, it's all about the control. So how do we do the control? So we have to keep the phases aligned. And this is something, again, so I'm going to bridge my sort of astronomy, not so much cosmology, but astronomy with short pulses. If you do astronomy, you want, and it just came up in Adam's talk, why was James Webb better than the Hubble? It's because it used a bigger telescope. And so the Fourier transform in this case, it's just short pulses in the line of the direction that the wave is traveling, and astronomy's in the perpendicular direction, but it's the same thing. The smaller, tighter thing you want to focus to, the bigger the spectrum has to be to have as many angles as possible. So their frequencies, spatial frequencies, are the angle. But implied in that is that the phase front is perfect, okay? So I'm showing that red, perfect spherical phase front, which came from that perfect flat line being curved by the telescope. But it was one of my optics colleagues, James Wyant, who was one of the first people to show that if the telescopes are on Earth, that beautiful phase front gets distorted by our atmosphere, and he was able to use real-time interferometry. This is not the actual interferogram of that. I'm just showing a random interferogram of his. But he did real-time interferometry so that they could use a deformable mirror and take that warped kind of red phase front that you see and change the mirror curvature so that you could get this nice flat phase front, and then you can get your great focusing. So we do the same thing. That's supposed to be pink, not red. But anyway, it's going to be not just perfectly red, it's going to have a lot of colors in it. We're going to hit a grading, which is the same as a prism. It takes all the colors and goes in different directions. Once we have each of the colors going in different directions, we can then use a lens. And that takes, each of the colors start at the same spot, so they each now, after a lens, point in the same direction. But you'll see that each color comes off the grating as a collimated beam, and that means it focuses at the focal plane. So you'll see that every one of our colors actually is going to come to a focal point. And so this is what we do. We do this control because just like the telescope has the problem with the atmosphere causing problems, so the atmosphere, every piece of optics that we have causes problems with keeping those phases coherent and phased with each other. So we do something, we could use a deformable mirror, we don't, I'm out of time. So we do use things like liquid crystal displays so that each point can have its phase attached, and then we just undo it. So if we start with a pulse that isn't short, our goal is to get a pulse that is short, and that's how we get a short, intense pulse, and that's how we use the infinite to get the infinitesimal. Thank you very much.
I want to thank, first of all, for the invitation to come here. I feel very honored by that, and we'll be speaking about quantum computing and quantum simulation. And I think it's actually one of the most beautiful examples that we have at the moment where basic science, like quantum science, is moving over to a quantum technology. Since you are a diverse audience, we got instructions. I would like to start out with a few very general slides and then move on something specifically what we're doing at the moment and where we actually see how the field is going. I think it was Feynman, a long time ago, this is more than 50 years ago, who envisioned, programmable quantum machines surpassing classical computers or classical machines. And he wrote this paper that I guess is what we're trying to do right now, which is about simulating physics with computers, and that classical computers actually fail in this context. So the question that he asked was basically that, can we use classical computers to efficiently, and the emphasis is on the word efficiently, simulate quantum systems? And the answer that he gave was no. We cannot, and it has to do with the fact that nature is not classical, but rather on a fundamental level. Think about quantum material. It is, of course, quantum mechanical, and he made this famous statement: nature is classical, and if you want to make a simulation of nature, you better make it quantum mechanical. Feynman himself did not, hint at how to actually do these things in practice, but I think we are doing this thing at the moment, and we made a lot of progress, and I would like to tell you a little bit about these things. The reason, why classical computers find it hard to simulate is that in the classical context, think about a system of, say, spins or little magnets that we have. We always think about them as sort of cycling through different configurations. All spin can be up or down, some of them up and some of them down. Whereas quantum mechanically, what we have is entanglement. So we have a superposition, of all of these different configurations here, and this is even an exponential number. So this exponential number, this exponential large Hilbert space that we have here, this is the one that classical computers cannot handle, but quantum mechanics sort of by definition can. So in this sense, this is handling and manipulation of entanglement that we're trying to do in these machines, which is kind of the secret sauce, of what's going on. In the meantime, of course, we have learned how to build quantum mechanical computers or simulators, and this happens on various platforms. My own expertise is coming from atomic physics, so we as theorists came up with ideas how to, for example, use ions in ion arrays, where we use internal atomic states to store quantum bits or qubits. We've learned how to manipulate them with laser light. We have come up with ideas how we can make them interact and really engineer different kind of entanglement and make it completely programmable. This has also been done with neutral atoms. This has been done also with solid-state systems like superconducting qubits. So there's a plethora of things out there where this paradigm of quantum mechanical machines that are universally programmable has become reality. Of course, the big challenges that we are facing at the moment is this, that we have on one hand this question of controllability. I mean, the more you scale up the system, and you really have to scale it up to benefit from all of these ideas, the harder it gets to do this kind of control. But the other part, of course, is also that you have to isolate your system very well from the environment. There's decoherence, and decoherence is, basically destroying these, very fragile entangled states which we have. And, so in this sense, one might say that the big, challenges that one is facing at the moment, what are the current frontiers, is this, that, one is at a point at the moment where these kind of machines are able to solve problems that are really, beyond what classical computers can do. We call this quantum advantage. And of course, we are always on the search of different algorithms, and I'm coming back to this thing in 1 minute, to find different applications. And of course, the hot topic right now, and this would really need a lot of time to explain the details for that, would be to do error correction and fault tolerant quantum computing. There's been a lot of progress, in particular with superconducting and also atomic systems, recently demonstrating that we have error correction, how these things work in the lab. And I think that that's a big stepping stone, which is taking us one step closer to this vision, even though, of course, will take a much longer time. The question is, of course, are these things useful for anything? And I guess that Feynman, to some extent, gave us the answer, that simulation of quantum materials, in the most general sense, that we would like to build quantum simulators, for example, as special purpose quantum computers, and to design new materials. High DC superconductivity is always mentioned over here. Maybe there's also drug design, and at the end, maybe we can also have some impact in whatever way on fundamental physics, simulating problems on these quantum machines, quantum problems that we find difficult to solve otherwise. What I would like to do now is sort of tell you in a few words, what we're doing right now at the moment, and this has to do with the fact that we would like to sort of rethink quantum simulation and lead it maybe one step closer to the fact that we would like to do something useful. And this is, I would like to tell you in a few words now, the story of quantum simulation that we do right now, and what we envision could be one of the coming things to think about, which is this inverse quantum simulation. I'm using sort of here the language of machine learning, where there's forward and inverse, and you will see that in a minute. So what we are doing at the moment, and I come back to this with the next slide also, is this, that we have sort of the understanding that quantum simulators that we are building right now, we are under quote sort of solving quantum many-body problems like the one in chemistry or whatever. There are, so many out in physics, of course. And in this sense, we create synthetic programmable quantum matter. But the way that we are doing these experiments at the moment, right now, in a very successful way, is more that we use them as a tool for exploration or discovery. But I think that the whole field right now is at the point where we can actually turn this whole story around from exploration to an active design, and I will explain to you in a minute what I mean by that. But I think what's really happening here at the moment is this, that we're asking the question about utility, of quantum simulation of this quantum machine. We have a quantum machine that has potentially a quantum advantage. And of course, we have all of these classical tools available like machine learning. And they are sort of coming together in this idea of inverse quantum simulation. And I want to just have now 2 more slides to talk about these things here. So what we normally do in a quantum simulation experiment is sort of indicated down here. You might have some quantum material that you would like to simulate, or whatever your many-body problem is, equilibrium, non-equilibrium. And the way how we in physics proceed is this, that we encode, of course, the knowledge of this material. We write down a model, a Schrödinger equation that has a Hamiltonian, a many-body Hamiltonian, maybe spins living on the lattice, as is indicated over here. And then we put this Hamiltonian, we program our quantum simulator that can be done digitally or also analog to get, at the end of the day, maybe some phase diagram. And I've drawn here the example. Well, maybe you would like to have a D-wave high DC material that you emulate, maybe with a Fermi-Hubbard model, that you got an optical lattice over here. So it's always of the type, we have a microscopic description, we sort of, under quote, solve the problem on the machine, and we got emergent properties. What I'm sort of proposing over here is that maybe we should actually turn the story around. That this is this inverse quantum simulation, where maybe one of you would like to draw a phase diagram as a kind of a wish list, or make a list of properties. Certain susceptibilities, and there could be a long list of properties. And maybe then we should ask our quantum machine, what does it take in order to realize this corresponding material? And this would mean essentially, that we would like to learn, sort of going now from the right here to the left, the Hamiltonian, which underlies the phase diagram that you have on the right. So we've moved over from an active exploration, where we go from left to the right, now to an active design, where we are asking the questions, this wish list over here, that we encode the properties that we want in the cost function, but then we do, for example, techniques like machine learning of Hamiltonian learning over here. That's sort of the basic idea. I think that the field is ready for these kind of things here. And, we have here a paper on the archive, very recent one, and we have done here different design cases to enhance certain properties of material, all the way to, you write down the spectrum, what kind of a Hamiltonian does it take. This has been a very active field in the context of classical computation, but we, of course, believe that quantum machines are more powerful, so I'm able to contribute along these lines over here. And this leads me to my last slide over here. I told you a little bit about, we are building quantum machines at the moment. We find them very promising, and I think we are sort of moving now on to the stage where we are trying to make these machines not only having fun in basic science, but maybe also leading over to the point where we can try to do something useful that corresponds to our original promise beyond the basic science that we do. Thank you very much.
I want you to get inspired by this picture. This picture shows single rubidium atoms directly seen with a microscope, and each spot is a single atom at a temperature of a few nanokelvin, 1 billion times colder than interstellar space. So I want to repeat what Bill Phillips told us yesterday, this quote by Erwin Schrödinger, where he said, as late as in the 50s, he, one of the developers of quantum mechanics, that the concept of doing experiments with single atoms is just ridiculous. But we are now doing single atom physics, and single atoms is also what enables us to explore quantum technologies and quantum computers. So this picture was taken in one of my labs at MIT. You see sort of a bunch of lasers, electronics, and all that. And on the right-hand side, you see the key piece, this high-resolution optical microscope, which allows us to see in this enormous clarity single atoms. And this just shows you another of my labs where we do experiments with cold atoms. So this is still tabletop experiments done by students who explore new quantum science. So what is important is, for our understanding of nature, is particle-wave duality. And particle-wave duality is already in general culture, as you see in this cartoon here. Actually, I shouldn't show this cartoon in the United States anymore because it gives such negative associations. But I also like if science makes it in popular culture. But if you carefully read that, there is one thing wrong. Because the policeman thinks the particle, because particle and wave has two identity cards. But the reality is all particles or photons have particle-wave duality, but they're rather like Superman. They have two identities, but never at the same time. So we want to explore with our microscope that those are not just particles, little dots, and they are also waves. So what we observe is, we observe a pattern of those nanokelvin atoms, and then we compare with a randomly generated, computer-generated speckle pattern, a white noise pattern, and you cannot see it with the naked eye, but if we analyze the atoms, we find a length scale, we find something characteristic which we can extract in our data analysis, and this is the wavelength of the atom. So we can show with those pictures that the atoms have actually an underlying wave nature. Particle-wave duality has also played a very important role in the development of quantum mechanics. And what is very famous is this debate, the controversy between Bohr and Einstein. And Bohr's and Einstein's controversy was about this double-slit experiment. Einstein said, if you have light which goes through the two slits and forms an interference pattern, that he thought it's possible to both measure the path of the light, which would be particle characteristic, and the interference pattern, which is the wave nature, whereas Bohr said, no, only one of them is possible. And Einstein came up with this ingenious construction. If you have a movable slit which has springs attached to it, if a single photon goes through, the slit will move a little bit, and this is how you measure the path, and then you can still observe the interference pattern. But Bohr clearly showed that this is not possible because of the Heisenberg uncertainty relation. So we have recently used nano-Kelvin atoms and have done an idealized implementation of this Bohr-Einstein idea. Each slit is now replaced by a single atom, and we scatter a single photon. And what we observe is sometimes when a photon is scattered by an atom, the atom is rustling like, the leaves in the wind. And this is then a measurement, and in this case there is no interference pattern. And since we have such good control over single atoms, we can now study that, and we can adjust by the size of the atomic wave packet whether they rustle all the time or only rustle in half of the time. So in that sense, we have done the most idealized version of this Bohr-Einstein-Gedankenexperiment, and I'm really wondering what Bohr and Einstein would have said if they had seen our experiment. So let me end on the note that I showed you single atoms. I showed you how single atoms lead us even today to a deeper understanding of quantum mechanics, how we can now do foundational experiments with single atoms, which Bohr and Einstein only dreamed about. But those atoms are also the building blocks of quantum computer, which Peter Zoller mentioned in his previous talk, and ultra-cold atoms are also used for the world's most accurate atomic clocks. These atomic clocks have now an accuracy of 10 to the minus 18, which is half a second in the age of the universe. So what can you do with an atomic clock which has a precision of 10 to the minus 18? Well, if you have an atomic clock and another clock which is 1 centimeter higher, because of gravity, because of gravitational redshift, because of general relativity, you can measure a difference in frequency. So this is now allowing ultra-cold atoms to have applications in geology, and in principle, you could even monitor an early warning system for earthquakes, because you can measure with very high sensitivity if the crust starts to move, because two atomic clocks differ in a frequency when they move 1 centimeter apart. So with that, I want to show you how maybe useless research on single atoms has applications, but nobody had ever thought to work with single atoms, observe single atoms with those applications in mind. The applications emerge from the fundamental research.
All right, so Adam has already talked a little bit about cosmology, so I thought I would go into something a little more astronomical and current. And so I want to talk to you about a new way technology can be used to do science, but also do something useful, so to speak. And this is a project known as ATLAS, the Asteroid Terrestrial Impact Last Alert System, which is a program to essentially monitor the entire sky many times a night. And it is able to do it right now in its first incarnation by having telescopes, quite small telescopes, powered with very large digital cameras scattered around the globe. And so, as I said, right now, these telescopes scattered around the night have a 100 million pixel digital camera attached to them. They're quite small, about 50 centimeters across. and they can observe something on order of 50 times the moon at a pop. And so every night, these things automatically go shifting through the night sky and take an image of essentially everything. Now, why was this project undertaken? Well, many reasons, but this is probably the main reason why NASA is funding it. I take you to Chelyabinsk, Russia in the 13th of February, 2013, when an 18-meter asteroid that weighed roughly 9,000 tons crashed into Earth, releasing roughly 500 kilotons, so that's about 25 to 30 Hiroshimas of energy. This is not a super rare event. It is one that happened to hit over the top of a city. And we know very well of another very big event that also hit Russia. It's obviously the largest landmass that was substantially larger. In any given year, you can expect there's about a 2% probability of something at least as large of this impacting Earth. So it would be good to know what these things are, because one could imagine getting unlucky and having such an explosion be confused, for example, with a nuclear explosion in this hair-triggered world that we live in. So you can go out and look by taking many images, and in 2024, Atlas discovered this object known as 2024 YR4. And it was soon realized that this was going to approach Earth very closely in 2032. And by taking many, many images with the largest telescopes, including James Webb Space Telescope, over the period of about 3 months, it was realized that fortunately it was going to miss Earth in 2032. But at this point, it still has a 4% chance, it turns out, of hitting the moon in 2032. So it comes back near the Earth in 2028. We will get a good view of it. That'll allow us to tighten up its orbit to a very precise measure. And I will say it will be quite spectacular if it does hit the moon. As I said, it's only a 1 in 25 chance right now. And probably will create quite a big mess for all the things that we're putting up to orbit the moon, and will create almost certainly an amazing show here on Earth, especially of all sorts of shooting stars coming down as the dust settles. So it's 30 times more massive than Chelyabinsk, and so if it had hit, it would have been quite an event, and it's the type of thing you really want to know about. So what can you do? Well, here is a similar-sized rock that was hit with a big hunk of metal off a NASA rocket. But the idea is you measure things to figure out exactly what they're going to do. Hopefully you'll have time and you can deflect, as this DART mission did. And we have a pretty good idea of how well that would work if you have time. And if it's going to hit over land, you would evacuate, because you will know where these things come, maybe only 7 or 8 days in advance. But it's better than not knowing at all, or prepare for tsunami if it's landing over the oceans. So keep looking. Ideally, 3 or 4 times a night is how you really know what's going on. And it's not a particularly big project these days. But it is a global project. It needs telescopes around the Earth. And these are where the telescopes are now. There's a very big hole right now where we have a blind spot. And so one wants to go down and put your telescope in a clear part of the planet. Blue here is clear. But you also want to put it in a dark part of the planet, so probably sticking it here in Dubai would not be your first choice, even though it's quite clear here most of the time. So we have a new range of telescopes we can build, where we put together a big telescope made out of a bunch of little ones. And so the technology that astronomy has developed in the form of digital cameras and optical systems has been mass-produced for amateurs. And now they're so good and so cheap, for about $1 million, we can make a telescope that can scan the entire sky each night, 1 million times fainter than the human eye can see, which is about as faint as the Palomar 5 meter could see in 1975. And ATLAS does not just discover Earth-impacting asteroids, it discovers comets, such as this very bright one a few years ago. It discovers interstellar asteroids like Atlas 3I, which is not an alien spaceship, but certainly got people talking. And for me, as someone who likes to work on the thermonuclear detonations in space, supernovae, it discovers every single one of them in the nearby universe, literally hundreds of thousands of them now, such that we can go through and understand the physics of these objects, continue to use them to measure extremely good distances for cosmology, but also understand the origin of all the elements, almost all of which the things in this room are created in these explosions. So, we're looking to expand the array. We'd like to see 12 sites eventually, and doing our best job now to go out and raise money. It's a little challenging because you kind of got to get people from around the world to work on this. And we need to do it because, as they say, you can expect a Chelyabinsk-like thing probably every 20 years or so. And if one happens to be landing on to a populated part of the world, it's going to cause a lot of problems. And these are things that we can stop. Thank you very much.
Okay, I'm going to talk about quantum mechanics. And we're in now what we're called the second quantum revolution. Well, what is that? It's now 100 years since modern quantum mechanics was formulated, and the laws of quantum mechanics haven't changed since this early period. And all the tests of them have shown so far that they're correct. But the key thing is, just because we know the laws of quantum mechanics doesn't mean we know immediately all the kind of strange things that can be done with quantum mechanics. It took a long time to understand fully what we could do with electromagnetism, well after Maxwell had finished his equations, and that led to a whole technology of the last century. Okay. So as I say, people now think we're in the second quantum revolution, and this is where we've actually changed our main view of quantum mechanics, which originally people would have thought quantum mechanics meant the Heisenberg uncertainty principle, interference, but now it seems that the property of entanglement is the property at the heart of this second quantum revolution. And it's actually a property pointed out, a central property of quantum mechanics pointed out by Einstein, and it was a thought experiment and an attempt to suggest that quantum mechanics couldn't possibly be a correct theory on a fundamental level, but now it's viewed as the fuel of the possible future quantum information processes. So, of course, Einstein got his prize not for relativity, but for his early contributions to quantum mechanics in the photoelectric effect. But by 1935, he'd fallen out of love with quantum mechanics. And he pointed out this entanglement property, which he called spooky action at a distance, but which Schrödinger now calls it entanglement, is a much more neutral term. This was a property that if I have two quantum systems, which are like a spin up and a spin down, that are well separated, but started off in a joint quantum state, if I do a measurement on this one, it implies what would be the result of a measurement on the other half of the system a long way away. And Einstein thought that was some kind of violation of relativity, but in fact it isn't, because there's no actual information flowing between the distant systems. So Einstein thought that if his thought experiment was carried out, it would eventually show that quantum mechanics was not a true description of nature. But we now know, of course, that the experiments were eventually done, and they led to a Nobel Prize in 2022 for rather old work, starting off with John Clauser, who took John Bell's analysis of Einstein theory, of his experiment, and did the first work on it, and a more fuller experiment later by Alan Aspey. And so quantum mechanics was correct, and it showed entanglement does exist over large separations. They managed to achieve that with photons, light, which can travel long distances without interacting with the environment. But the problem with entanglement over long distances as opposed to atomic distances is it's very fragile against decoherence. So if we want to work with it, we have this problem of fragility. So quantum mechanics has continued to deliver surprises. And one of the surprises, at least for me, that I was involved with was this, what's now called topological matter. So what's this topological matter? We can say that it differs from ordinary matter because it's got some property, which in some sense is related to entanglement properties, which can be described by a whole number, an integer. Maybe ordinary matter is described by a boring number like 0 or 1, which maybe not really that boring mathematically, but if the state of matter is described by a different whole number, there has to be a boundary between the regions where it has a non-trivial number and the trivial number. You can't go continuously from 0 to -2, as in this picture. So the topological matter often has this very interesting kind of edge states at the boundary between the regular matter and the topological matter. And it also has a kind of robustness because you have to do a certain amount of damage to something to change it from -2 to 0. And a classic example in mathematics is this classification of closed surfaces by the number of holes in it. So the number of holes in a surface, like a donut, is clearly, at least on a scale much larger than an atomic scale, where you can think of the donut as a smooth object. The number of holes in it is a topological number. You can have 1 hole, 2 holes, but you can't have 0.6 of a hole. Okay? And these kind of topological properties, they're kind of robust against change. To change a football into a bagel, I have to punch a hole through the middle of it, which requires a certain amount of work and destruction to be done. So this is a kind of robust property, and it's at least been hoped that we can use topological materials to use their robustness to protect us against loss of their quantum state or loss of the quantum information to the environment. So most of these kind of new discoveries in quantum mechanics are kind of unexpected and accidental. No one really had thought about this topological matter idea until it emerged. And my own work, for a whole lot of interesting accidental reasons, took me in the neighborhood of this problem. And it was a problem very kind of abstract to do with a quantum magnetic system. But before, people thinking about magnetism really hadn't built entanglement into their pictures of magnetism. And it turned out that in the system I looked at, entanglement played an interesting role, that instead of the atoms, the magnetic atoms just being lined up with their magnetic spins pointing up and down, the magnetic spins kind of separated. A spin 1 atom had 2 spins coupled in the parallel state. They kind of separate to form a bond, and half of the spin is left at one side of the atom of the chain, and the other half at the other side of the chain. That turns out to be typical of this edge. The edge between the entangled region and the unentangled region has this spin 1/2, which is half of the original spin left there. Okay, this was actually pretty controversial at the time for kind of internal reasons in the magnetic community, but it led to a lot of controversy, but controversy is always very good in science, and lots of new methods, both theoretical and experimental, were used to weigh in on this controversy. And finally, one of the key things in modern materials is that now the material scientists have got so good they can actually build the toy material, the toy models that theorists use to play with and find interesting things in. So this was And the basic picture, topological picture, is rather straightforward. If I think of a line of people with their joining hands, hands usually come in pairs, but then there's a free hand left over at each end of the chain. So where's that got to do with the more modern developments? Well, there's an amazing thing called Majorana zero modes, which go back to ideas of Majorana, who was one of the, I guess after the early quantum mechanics, he came up with this so-called Majorana fermions, which are essentially splitting a fermion into a real and imaginary part. And basically, it has a remarkable feature that you can think of an orbital, a box, which is either empty or filled as a qubit. It has two states, empty or filled. And the amazing thing is you can pull this thing into two half boxes. When you split the box up, the orbital, you can't see anymore whether it was initially empty or filled, so the information in this qubit has been hidden from the environment. And this is actually at the heart of at least one attempt to build a quantum computer, the Microsoft one, which is attempting to use this to have topological protection, which would, if it can be made to work, would on paper at least solve some of the problems of decoherence. So anyway, this is Microsoft have announced an architecture for this, but it's not quite clear how much it actually is working. So the jury is out on this thing, but it's an attempt to do this thing. And so how does this work? It actually relates to the original spin chain I showed you, that we couple a one-dimensional system, in this case a chain of atoms, to a superconductor. And this Majorana idea that you can split an electron orbital into two parts, a real and imaginary part, which are here purple and green, has the feature that when you apply a superconductor to it, you can re-zip together the real and imaginary parts, but using from neighbors, and get left with half a Majorana zero mode or half an orbital at either end of the chain. And so this is a kind of rather amazing idea in quantum mechanics. It's been shown at least virtually in simulations with qubit arrays. And we're still waiting to see whether it will actually lead to any kind of quantum computing devices. So finally, that's just one of the attempts to build a quantum computer, but there are of course many other which are progressing much further, much faster. Nitrogen vacancies in diamond, ion traps, transmons, etc. But finally, quantum computing is not the only new development coming out of this new study of qubits. Where actually, the qubits coupling to the environment can be enhanced to do incredibly accurate measurements. And we heard that either by letting atoms drop, you can measure the gravitational field very precisely, maybe detect mineral deposits. And the other thing is just measuring magnetic fields with these qubit devices like nitrogen vacancies in diamond have been proposed to give you a fingerprint to the Earth's magnetic field at each point on the surface of the Earth that you could then substitute for GPS to use AI to give you a fingerprint and tell you where you are in case the GPS is shut down for some reason. So finally, there's a lot of new developments in quantum, and thank you.